In this video, we're going to look at similar trying to find zeros and solving inequalities, but we're going to look at polynomial functions outside of quadratics. So in the last video, we focused only on quadratic functions. Now we're going to expand that to polynomials of degree greater than 2. So a polynomial function can be factored to find the zeros. Sometimes this is very straightforward, especially if it's a quadratic or we've got a polynomial of 4 terms that can be factored by grouping. But that's not always going to be the case. But let's just review finding the zeros of polynomials that are not a power of 2, not a degree of 2. So we have x to the 4th minus 8x squared plus 15 equals 0. So this is similar to a type of equation we've seen in the past. This is set up in quadratic form. So we can use u substitution to help us visualize the factors of this a little bit easier. We're going to let u equal x squared. So then this becomes u squared minus 8 times u plus 15 equals 0. And now this looks a lot more manageable to factor. Our first terms are u, and then our last terms are going to be factors of 15 that sum to -8. So 5 and 3, we want them both to be negative. And we can set each of these factors equal to 0. We get u is equal to 5, or u is equal to 3. And now we back substitute u is equal to x squared. So x squared equals 5, or x squared equals 3. To isolate the x in each of these, we're going to take the square root, remembering to add plus or minus when we take the square root to solve for a variable. So this gives us x equals plus or minus the square root of 5. Same for our other equation, taking the square root of both sides, adding plus or minus. We get x is equal to plus or minus the square root of 3. So this polynomial has 4 zeros, which we could also represent these as ordered pairs. 4x cubed plus 2x squared minus 2x minus 1 equals 0. Here we've got a polynomial of 4 terms. We're going to try factoring by grouping. We're going to keep them grouped exactly the way they are. You could rearrange your terms if you felt like it was going to be easier to factor that way. So from our first set of our first grouping, 4x cubed plus 2x squared, we can factor out a 2x squared. And when we divide 2x squared out, we get 2x plus 1. From our second grouping, we can factor out a -1. And we're left with 2x plus 1. And we know that we've been successful with factoring by grouping when these two factors are the same. Since we have a like factor of 2x plus 1, we can factor that out. And our second factor is going to be 2x squared minus 1 equals 0. And now we have two factors. We can set them both equal to 0 to solve. 2x plus 1 equals 0, or 2x squared minus 1 equals 0. I opted to write both of these out. The first one I can solve in my head, x is equal to -1/2. But this second one, because it is quadratic in nature, I'm going to take my time and go through the steps. So I've got 2x squared equals 1. X squared equals 1/2. And when I take the square root of both sides, I need to add that plus or minus. So we get x is equal to plus or minus, the square root of 1/2 is equal to plus or minus 1 over the square root of 2, which to rationalize, I'm going to multiply by square root of 2 over square root of 2. Since we've already finished our trig unit, that ratio should be very familiar to us. This is going to be plus or minus square root of 2 over 2. So this is some examples where factoring a polynomial that's more than degree 2 is pretty straightforward, but that's not always the case. So if a polynomial of higher degree, we can't factor it using one of those two techniques, we use what's called synthetic division to find some zeros. So let's do a quick review of synthetic division. We want to divide the polynomial 3x cubed plus 11x squared plus 8x minus 4 by x minus 5. Now, just a quick reminder, we can use synthetic division when we're dealing with a divisor of linear form, so this x minus 5, and we really do want that coefficient on our divisor to be 1, or the coefficient on x to be 1. So it's an x plus or minus some constant. We cannot use synthetic division if it's a quadratic divisor at all. So what we're going to do to set up synthetic division, we've got the value of our c, which is actually going to be the opposite of this 5, negative 5, so it's going to be positive 5. And then we set up our coefficients, so 3, 11, 8, negative 4. And another reminder, if you're missing a term in your polynomial, so what we're talking about is x cubed, x squared, x constant. If you're missing one of those terms, you do need to have a placeholder. We don't need one in this case. We bring down that first coefficient, and then we multiply 3 times 5 is 15. And then we add vertically. 11 plus 15 is 26. And now we repeat the process. 26 times 5 is 130. 130 plus 8 is 138. 138 times 5 is 690. And 690 plus negative 4 is 686. So this is just a review of synthetic division and how we go through that process. Let's try this again, but divide the same polynomial by x plus 2. So that changes the number I have in my little box to a negative 2. Again, we're always using the opposite of the sign inside that linear divisor. We have our coefficients, 3, 11, 8, negative 4. Start by bringing down the 3. 3 times negative 2 is negative 6. 11 plus negative 6 is 5. 5 times negative 2 is negative 10. Negative 10 plus 8, negative 2. Negative 2 times negative 2 is positive 4. And positive 4 plus negative 4 is 0. So looking at both of these, what do these results mean? Well, I'm going to focus on that second example. Since the remainder was 0, and if you remember from synthetic division, this last value is always your remainder. If the remainder is 0 when dividing by that x plus 2, that means that x plus 2 is a factor, and x equals negative 2 is a 0. So what I've summarized here is actually what we call the factor theorem. So that's something that you would have learned in college algebra. But basically, when we divide and we get a remainder of 0, that tells me that whatever we were dividing by is a factor and that it results in a 0 of that function. So that tells me that f of x, so looking up here, we have f of x is equal to x plus 2. And our second factor comes from those coefficients when we used synthetic division. It's going to be 3x squared. Goodness, got very heavy. 3x squared plus 5x minus 2. And you could continue to factor that 3x squared plus 5x minus 2 as well, if possible, to get it to write f of x as a product of linear factors. Thinking about that first example where our remainder was not 0, obviously that tells me that x minus 5 is not a factor of that polynomial, but it does tell us something very interesting. If the remainder is 686 when dividing by x plus 5 or x minus 5, then I know that f of 5 is equal to 686. And this is a quick summary of the remainder theorem. Now, coming back to the idea of trying to find our zeros, we also have the rational root theorem, which tells us that if a polynomial has any rational roots, they're going to be of the form p divided by q, where p is some factor of the constant term and q is some factor of the lead coefficient. So we can narrow down what the possible factors or rational factors could be for a polynomial by finding all the possible ratios p over q. F of x is equal to x cubed minus 2x squared minus 11x plus 12. So using that rational root theorem, we're going to try to find the zeros of this polynomial. So P are going to be factors of our constant, so 12. So P could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. All of these are factors of 12. Negative 1 times negative 12, positive 12. 1 times 12, 12. So on and so forth. Q are going to be factors of 1, which are just plus or minus 1. So our possible roots, P over Q, are going to be all of the ratios set up, plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, so on and so forth, which results in that same list as we had for P. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. That's like 12 different values, okay? We're going to just start testing some of these values using synthetic division. I'm going to start with 1 because it's easy. So 1, my coefficients for my polynomial are 1, negative 2, negative 11, and 12. Bring down the 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times 1 is negative 1. Negative 11 plus negative 1 is negative 12. Negative 12 times 1 is negative 12. 12 plus negative 12 is 0. We found a remainder of 0, which means that one of the factors of f of x is x minus 1. And the other factor comes from those coefficients we found through synthetic division. That's going to be x squared minus x minus 12. And we can factor that quadratic. Factors of negative 12 that sum to negative 1. It's going to be negative 4 and positive 3. And now that f of x is written as a product of linear factors, we can see all of the zeros. Our zeros are going to be 1, 4, and negative 3. Now, we could have kept doing synthetic division, and there are times where you have to go through this process because we lucked out. The first value we tried happened to be a 0 of our function. But that's not always the case. So you could potentially be going through synthetic division multiple times before you find a 0. And once you find that 0, then you can typically apply other factoring techniques and you don't need to continue doing that, but you could if you wanted to. Now, applying this back to the idea of the inequalities, we don't have any examples built in, but once we have all of our zeros, those are the critical points, and we can use our sign chart to solve inequalities, just like we saw illustrated with our quadratic inequalities in our previous video.